Welcome back to Basic Electronics. In this lecture, we will continue to look at the precision clipper and clamper circuits, which we saw in the previous lecture. We will also take a second look at the half-wave rectifier based on the super diode, and in particular, look at its response to an input signal with a relatively high frequency. So let us begin. Let us simulate the circuit that we just looked at, this circuit here, and verify its operation. To begin with, let us get the components that we require. We will use a 741 op amp. Resistors, of course. Then we require a diode. We will use a SPICE diode model. We require a DC voltage source for VR, that is called VSRC DC. We require an AC voltage source as the input voltage, that is VSRC AC. And we also require the reference node, that is ground. Alright. Our next step is to make the connections. So let us do that. Okay. Let us now assign the component values. This resistance can be 1K, and we will consider the case in which RL is much larger than this R here. So RL could be, let's say, 1 mega ohm, like that. This VR could be 2 volts. Later we can change it if we want. This is our input voltage. We can make the amplitude equal to 5 volts and select a relatively low frequency, let's say 50 Hertz, because the 741 op amp is not going to work at high frequencies. We can also display these values. So this has an amplitude of 5 and frequency 50 Hertz. Alright. Our next step is to define the output variables. We will define two output variables. One, the input voltage, and the second, the output voltage. We can change these names, V in and V out. Alright. We can now go to the solve block section and define the solve blocks. Let us now define our solve block. We want to do transient simulation, so we need to change this DC to transient, like that. Our time period is 20 milliseconds, so let us say we simulate for 2 cycles, that is 40 milliseconds, with a time step of 0.02 milliseconds, a small time step compared to the period. And we now need to get the output block. In the output block, we will select both V in and V out. Okay, let us run the simulation now and look at both V in and V out together. So this is what we have. Let us look at only the steady state part. So if Vi is less than 2 volts, this part here, our Vo is 2 volts, that is Vr, and otherwise Vo is equal to Vi, as we would expect. Here is our second circuit. The only difference between this circuit and our previous circuit is that the diode has now been reversed. Let us see what it is doing. First, when the diode conducts, the feedback path is closed like that, and we can expect V minus and V plus to be nearly equal, and since V plus is equal to Vr, V minus is also equal to Vr, and since Vo and V minus are the same, we have Vo equal to Vr. Let us now look at the diode current, and in particular let us write the KCL equation at this node. Here we have three currents, ID, this current and this current, which is the same as the current through R. That means ID plus VR by RL, that is this current, since VO is equal to VR, plus this current, which is equal to VR minus Vi divided by R. That should be equal to 0. Now, since the diode current can only be positive, we get this condition, minus VR times 1 over RL plus 1 over R plus Vi by R greater than 0, and that implies that Vi must be greater than VR times R plus RL over RL. Once again, let us define this quantity as Vi1, and since this factor is greater than 1, Vi1 is generally greater than VR. Alright. In the other case, that is Vi less than Vi1, the diode does not conduct, so we don't have this current here, and Vi then divides between R and RL, and Vo is given by voltage division. So Vo in that case is RL by R plus RL times Vi. So to summarize, if Vi is greater than Vi1, the output voltage is equal to Vr. Otherwise, the output voltage is RL by R plus RL times Vi. Here is the graph of Vo as a function of Vi. This is the Vo axis, that is the Vi axis. If Vi is greater than Vi1, that means this region, Vo is equal to Vr, a constant. Otherwise, we have this straight line which passes through the origin and has a slope of RL by R plus RL. So this circuit is also a clipper, and it clips voltages which are greater than Vi1. And once again, as a special case, let us consider RL to be much larger than R. In that case, our Vi1 is equal to Vr because this factor becomes equal to 1, and the slope of this straight line also becomes equal to 1. Let us simulate the circuit now and verify that the functionality we have predicted is actually observed in the simulation results. This is our previous circuit. All we need to do now is to reverse the direction of this diode. So let us do that. We select the diode first, Control X, Control V, and now we can reverse the diode by pressing R 2 times. make the connections. We need to add this node voltage here as the output variable. So let us do that, and we'll call that V out. Alright, let us now go to solve blocks. We need to add V out over here in the output variables. And now we can simulate the circuit. Alright, so that is our result. And as we expected, if Vi is greater than 2 volts, that is Vr, our output voltage is constant, that is equal to Vr. Otherwise, Vo and Vi are equal over here. So we have looked at two of the circuits so far, this one and this one, and they are both precision clippers. That means the diode voltage drop V on does not appear in the Vo versus Vi relationship. Let us proceed further and look at these other two circuits. Here is our third circuit, and we have a capacitor now. Let us see what it is doing. We have defined the capacitor voltage with plus here and minus here. If the current through the capacitor flows in that direction, then Vc will increase. If the current flows in the other direction, like that, then Vc will decrease. Now the key point in understanding this circuit is that if the capacitor voltage has to decrease, the current has to flow like that, and that can only happen if the current flows through RL, because the diode does not conduct in that direction. So the time constant for the discharging process, that means the process of decreasing Vc, is RL times C, because the diode is not in the picture. And if RL times C is much larger than 1 period of the input voltage, then in a given cycle Vc can only increase. So that is a very important conclusion, and we can use that to see what this circuit is doing. Let us consider the interval in which the diode T conducts. When that happens, the feedback loop is closed. V minus and V plus would be nearly equal, and therefore V minus would be equal to Vr. And what is the capacitor voltage in that case? The capacitor voltage is V minus minus Vi, that is Vr minus Vi, or Vr minus Vm sin omega t. Now this quantity is maximum when this Vm sin omega t is minimum. And what is the minimum value of Vm sin omega t? It is simply minus Vm. So therefore we have Vc max equal to Vr minus Vm, or Vr plus Vm. And as we mentioned, once the capacitor voltage reaches this maximum value, it cannot decrease anymore as long as this assumption holds. And therefore in steady state we can say that Vc remains equal to Vc max, and therefore Vo, the output voltage, is Vi plus Vc, which is Vi plus Vc max, like that. That is equal to Vm sin omega t plus Vr plus Vm. And notice that the on voltage, V on of the diode, does not appear in this expression. Here is an example. The input voltage has an amplitude of 3 volts, so it varies between plus 3 and minus 3. This is our VR equal to 1 volt, and our output voltage is Vi plus VR plus Vm, and that essentially serves to clamp VO exactly at VR as we see in this plot. Let us look at the simulation results now. The capacitance we have chosen is 10 micro and RL is 10 kilo ohms. So RL times C is 10K times 10 micro or 100 milliseconds. Let us now see how that compares with the period of the input waveform. The input voltage has a frequency of 1 kilohertz. That means a time period of 1 milliseconds. So we have to compare 1 millisecond with RL times C, which is 100 milliseconds. So obviously 100 milliseconds is much larger than 1 milliseconds, and our assumption that RL times C is much larger than T is satisfied. Let us look at the plots now. The blue graph is the input voltage. It has an amplitude of 5 volts, so it goes between plus 5 and minus 5. The green line is our VR, that is 2 volts, and the red one is the output voltage. So as we would expect, the output voltage has the same amplitude as the input voltage, but it is shifted up such that it is clamped at VR, that is 2 volts. Let us now consider our last circuit. It is quite similar to the previous circuit, except the diode direction has been reversed. And note that we have indicated VC with a plus here and minus here. If VC has to increase, the capacitor current must flow like that, and if VC has to decrease, then the capacitor current must flow in the opposite direction like that. Alright, let us now consider the case in which VC is decreasing, that means the capacitor is discharging. Now the only way that can happen is if the current path is through RL and then through the capacitor, and that is because the diode cannot conduct in this direction. In other words, the time constant for the discharging process is RL times C, and if RL times C is much larger than T, the time period of the input waveform, then in a given cycle VC can only increase. Let us consider the interval in which the diode is conducting. That means this feedback loop is closed and V minus and V plus are nearly equal. That means V minus is equal to VR. And the capacitor voltage in that case is Vi minus VR, that is Vm sin omega t minus VR. And the maximum value of Vc is simply Vm minus VR. So Vc max is Vm minus VR. When the capacitor voltage reaches this maximum value, Vm minus VR, it cannot decrease as long as this condition is satisfied, and therefore in steady state Vc remains equal to Vc max, and the output voltage is then given by Vi minus Vc, that is Vi minus Vc max, or Vm sin omega t plus Vr minus Vm. And as in the previous case, the diode voltage drop V on does not appear in this expression for Vo of t. Alright, let us now look at the plots. This is our input voltage with an amplitude of 3 volts, so it varies between plus 3 and minus 3. That is Vr, which is equal to 1 volt, and that is our output voltage. So the output voltage in this case has got shifted downward, and it has got clamped precisely at VR. Let us look at the simulation results now. The circuit shown here is identical to our previous circuit. That means we have the same C value here, same RL, same frequency. The only difference is that the diode has been reversed. Here are the plots. This is the input voltage. It has an amplitude of 5 volts. So it varies between minus 5 volts and plus 5 volts. That is our VR equal to plus 2 volts. And the red graph is the output voltage. And as we expect, it has been shifted downward, and it has got clamped at VR, that is 2 volts. Let us make a few comments on the super diode circuit. Here are some sample waveforms. This is the input voltage. That is the output voltage. And the green one here is VO1, the op-amp output. Now when Vi is greater than 0, the op-amp operates in the linear region as we have seen before, and VO1 is VO plus VON. And when Vi is greater than 0, VO and Vi are the same, so therefore VO1 is equal to Vi plus VON, as we can see over here. When Vi is negative, the op-amp operates in the open loop configuration, and that leads to saturation, and VO1 becomes equal to minus Vsat. That is what we see over here. So in this region, the op-amp is operating in the linear region. Here it is in saturation region, linear region again, and so on. So this transition from negative values of Vi to positive values of Vi requires the op-amp to come out of saturation. For example, here the op-amp is in saturation, here it is in linear region. So at this point, the op-amp has to come out of saturation, and VO1 has to go from minus Vsat to whatever that is. Now this process is relatively slow, and it is limited by the op-amp slew rate, and this is a problem because this process is slow, and therefore we cannot operate this circuit at high frequencies. You can look at this sequel file and plot all of these waveforms. We have seen that the time taken by the op-amp to come out of saturation is a matter of concern, but if the input frequency is low, then this time is of no consequence and it can be neglected. Let us take a look at an example of that situation. Here, the input signal frequency is 50 Hz in this case, so the period is 20 milliseconds, and we don't really see any problem. This is our output voltage, and it looks like what we would expect. But at high signal frequencies, this time for the op-amp to come out of saturation leads to distortion in the output waveform. Let us see an example of that now. So here we have a signal frequency of 1 kHz, and we notice that there is a problem at this point. What is happening here? Vi is going from negative values to positive values. The op-amp is coming out of saturation, and it is taking some time to do that, and therefore we see this problematic waveform here. So clearly this is not a very desirable situation and should be avoided. And this effect shown here is very real, can be observed in the lab, and you should definitely hook up the circuit and check it out. To summarize, we looked at the precision clipper and clamper circuits. We saw that the diode voltage drop V on gets effectively eliminated in those circuits. We then looked at the speed limitation of the half wave rectifier circuit based on the super diode. and found that the speed is limited because the op-amp enters the saturation region. In the next lecture, we will look at a half-wave rectifier which overcomes this limitation. So see you later.